Okay, so now we'll briefly talk about what are called multiderivative methods. As the name implies, what happens with multiderivative methods is that you try to construct approximations of the exact flow map, not just by using combinations of the vector field, but you're also using derivatives of the vector field in constructing your approximation. So multiderivative methods rely on derivatives of the vector field. And perhaps the most common example you might have seen before is what is called the Taylor method. Okay, so for example, Taylor method. And as the name implies, the Taylor method is based on looking at the Taylor expansion for the solution, or basically just the Taylor expansion of the solution function, keeping in mind that the solution satisfies the differential equation, right? So you probably know that you can have a Taylor series, right? Yn plus 1 is equal to Yn plus basically the sum from I equals to 0 to m of basically h to the I plus 1 over I plus 1 factorial, and then the basically I plus first derivative of y evaluated at yn and tn. Okay, and then there's an error. Okay. Which has to do with the truncation error of the Taylor series. So, but nevertheless, you can construct an approximation just looking at the Taylor expansion and then truncating this. And then, of course, now you have this problem that you have derivatives of y, and you don't know what y is. So what you do instead, of course, is that you use the fact that you know that y dot is f of y and t, and so you can rewrite this as now derivatives of the vector field. Okay. Actually, I should just say that it's y, the I plus first derivative of y at the time t, right? But this thing here is equal to, now I'm going to use the fact that I know that y satisfies the differential equation to write this as the ith derivative of the vector field f, okay, now evaluated at yn tn. All right, so in principle, this is something that you can compute. So one immediate observation, if you will, is that unlike some of the other methods which we studied, like multi-step methods or Rogakuta methods, this does involve derivatives of the vector field. All right, so just given the formulation of the problem as an initial value problem where you know the differential equation and you know the initial conditions, you actually now further need to basically symbolically differentiate the vector field which is given to you. So the disadvantage immediately of multiderivative methods as a practical tool is that you have to put in the upfront effort of analytically computing these derivatives of the vector field. And so what that means is that for each problem which you have, each system of differential equations which you have to put in that effort. Okay, so in practice, it's not so common for people to sort of invest that amount of time. It's like on a problem, unless it's of particular interest, and you want to get methods which are either extremely accurate or fast. It's like for a very, very specific class of problems. So perhaps the most sort of important example, if you will, of circumstances where people have invested that time and effort into doing this are simulations of the n-body problem. Okay, and this is of interest, of course, when you're studying celestial dynamics. It's like stability of the solar system, and so in those instances, people really have invested a huge amount of time in sort of very efficiently computing derivatives of the vector field associated with the n-body problem. But in general, it's perhaps not such a common approach because, again, it's something you have to put in more upfront effort into, and it's something which requires you to do this for each different problem which you study. Okay, all right. So obviously, again, this comes from the Taylor expansion, right? Which says that y at some t0 plus h is approximately y at t0 plus derivatives, right? Some I equals to 0 to m. Well, actually I equals to 0 to infinity in general, right? Of h to the I plus 1 factorial, and then I plus first derivative of y at the time t0, right? Okay, so you might ask, well, how do you go about it? So computing derivatives of the vector field, okay? So of course you start off with the fact that y dot is equal to f of y and t. So you start off the initial differential equation, and then you use the observation that the total time derivative, d dt, can be written in the following way. Okay, so you can be written as the partial derivative respect to time plus basically the partial derivative respect to y, but you have to multiply this by the total time derivative of y respect to time. Okay, and then again you use the fact that you know what the total time derivative of y respect to time with, which is this vector field f of y and t. So the total time derivative operator looks like the partial respect to time plus f of t, well, f of y and t, dy, dy. All right, so it's a partial respect to time plus the vector field multiplied by the partial respect to the solution y. And you can easily convince yourself, especially when you have a differential equation which is non-autonomous, that the number of terms which show up in the nth derivative of the vector field, grows extremely fast. Okay, so let's just try to see an example of that. Right, so if you take the second derivative, y double dot, this is the total time derivative of f at y and t. Right, so but the total time derivative is the partial respect to time plus f of y and t times the partial respect to the solution. Okay, and then I have to apply this to f of y and t. Okay, so I'm going to omit the dependence on y and t. It's just to save a little bit of time, and I'm going to denote partial derivatives by subscripts. So this gives me the partial respect to time of f, right, plus f times the partial respect to y of f. Okay, so that's the second derivative. It's and again, it already involves two terms. Let's see what happens if you have the third derivative. Okay, so the third derivative again is the total time derivative applied to f of y and t. So this is going to be d dt plus f d dy applied to fy plus fy. Okay, so now it's we're going to have to use the product rule at least for the second term, and we have to distribute. Okay, so you have so if I take the partial of time with respect to fy, you get ft, you get ftt, right, plus partial time respect to this term. That's a product. We have to apply the product rule. So that's ft fy plus fty, right? And then we still have this term which distributes over. So you have fty. I'm going to assume the equality of mixed partials here, right? Plus this now applied to this. So that's fy fy plus one more term where I differentiate this second term. So plus, so let's see. So I have an f here, I have an f, and I have a fyy. Okay, so you can sort of see quite readily that it's like even when you're taking the third derivative, you end up getting a huge number of terms, and of course some of these things combine with each other, but nevertheless it's like it's fairly easy to convince yourself that it doesn't take too much. It's like in order for the number of terms you have to worry about to really sort of grow extremely fast. Of course, things are much simpler. It's like if there's no explicit time dependence, because then all the partial derivatives with respect to time would vanish, and then you have much fewer terms to contend with. Okay, but nevertheless, it's like hopefully it's like you'll see that in principle, certainly when you're dealing with a fully non-autonomous vector field, that the number of terms in the Taylor method grows extremely fast. Okay. So that's just sort of a quick observation, and I should say that the Taylor method is primarily used in numerical analysis as a means of analyzing the accuracy of other methods, and that's because the Taylor method gives you a way of systematically, informally writing down, arbitrarily high-order approximations of the exact flow map, and then what you do is that you compare the Taylor method term by term. It's like with basically expansions of other methods in order to determine the order of accuracy of the method. And so that's something which is really done quite often. So let me then briefly say also some other approaches one might have in constructing multiderivative methods besides just the Taylor method. And in particular, how multiderivatives might show up. It's like in the systematic construction of other type of one-step methods. Okay. All right. So let me sort of remark the following. As we've seen, right, you can use numerical quadrature applied to the fundamental theorem of calculus to obtain sort of numerical methods, right? Numerical ODE methods. So one observation is the following. It's like the methods which we talked about, in particular Newton cotes, and sort of the Gauss method. These involve quadrature approximations, which just involve evaluating the integrand at different points. But you can of course construct numerical quadrature rules which also use derivatives of the integrand in order to construct the approximations. Okay. As you might expect from Newton cotes, this relies on the idea of polynomial interpolation, where you don't just have access to the function, but derivatives of the function as well when you're constructing the approximation. And of course, it's like the simplest example of, again, a multiderivative approximation of a function is the Taylor expansion. Okay. But you can imagine a situation where you have access to derivatives of the integrand, but at a bunch of points, not just one point, which is the case of the Taylor method. And so that leads to the idea of Hermite interpolation. Okay, so there's this idea of Hermite interpolation, right, which allows you to construct sort of polynomial approximations using both function evaluations and derivatives, right? And so in particular, it's like this, there are sort of two extreme cases, right? There's the sort of Newton type interpolation where you have, again, just function values at a set of distinct points, and then you have the other extreme where you have all the data at just one point, but they involve derivatives of the function, which is of course just the Taylor expansion. And so I should just comment that one way to put both of these, it's like extreme classes of interpolation type methods together into a common framework is true what is known as divided differences. So divided differences sort of provides a framework for sort of combining sort of Taylor expansions and sort of traditional polynomial, say Newton polynomial interpolation into sort of a single sort of unified framework. So in principle, then, if you use that as your underlying interpolant for constructing numerical quadrature approximations, then you would naturally lead to a class of numerical ODE methods, which are then multiderivative methods. So that's another very systematic way, if you will, of constructing numerical ODE methods, which are multiderivative methods. Okay, so I'm not going to really talk too much about Hermite interpolation or divided differences, so you might have seen this before. It's like in an undergraduate class, and if you haven't, it's like I'll be happy to sort of point out some references which you can look up about this.